Hello, good afternoon, everyone, and welcome to Real Analysis. And I'll be discussing my part on our topic Lebesgue Measure, and that is Corollaries 3 and 4 and Proposition 5 of Royden 1988 in his book. So the discussant is yours truly, Mr. Japhet Enabaira, a PhD in Science Education, major in Mathematics student. So what is that corollary number 3? If A is countable, then M star A, or the outer measure of A, is equal to 0. So before we are going to show how this corollary works, first define what is a countable set. According to Royden in his book, a set is countable if it is the range of some sequence, meaning it is the image of a certain sequence whose domain is the set of natural numbers. Now, also many authors restrict the notion of countable to infinite but countable sets. There exists a bijection from that set to the set of natural numbers. If you're going to remember in our lesson in abstract algebra, that if we can establish a bijection or a one-to-one correspondence, onto and one-to-one, from a certain set, say for example, a set of integers to the set of natural numbers, then we can say that that set is countable or denumerable. So the other terms for countable set is the numerable set, also found in the book of Royden. So that's the definition of countable. So let's try to prove if A is countable, then the outer measure of A is really equal to 0. So we're going to use the definition of outer measure. So we have already discussed the definition of outer measure from my colleagues in the previous discussion. So when we say the outer measure of A, we're finding the infimum of the sum of the lengths just enough to cover A. So let us try to use this proof to prove that if A is countable, then M star A is equal to 0. Note that here epsilon is greater than 0. A is the sequence x sub n. So you can also write that as the set containing x sub 1, x sub 2, x sub 3, and so on until infinity. So that's a countable set, subset of real number, and M of A means outer measure of A. So that's this proof came from Baker and his colleague. Now, by definition, let us cover each sequence x sub n. So it's a subset of a real number by I sub n. So I sub n is the collection of all open intervals covering x sub n. So if I sub n covers x sub n, or the sequence x sub n, so we can say that x sub n is an element of I sub n. So if we're going to illustrate that in this number line, say for example, if the center is x sub n and we have x sub n minus e or epsilon over 2 raised to n plus 1, the interval of this 2 x sub n plus epsilon over 2 raised to n plus 1. So if we're going to consider this interval, we can right away see that x sub n is an element of this interval. Actually, x sub n is the midpoint, because if you're going to compute the midpoint, you just add and divide by 2, so x sub n is the midpoint. So basically, if x sub n is an element of I sub n, if we're going to consider the set containing n, that's an element of the set of the interval from x sub n minus epsilon over 2 raised to n plus 1 to x sub n plus epsilon over 2 raised to n plus 1. Now, what does it imply? It implies that the set x sub n, or the subset x sub n of real number, or the sequence, which is represented by A also, is a subset of the union of these open intervals that covers A. Now, if we can see the measure of I sub n, by definition of the outer measure of an interval, it's actually the difference, no? The difference of the endpoints. So if we're going to subtract the endpoints, the measure of the outer measure of I sub n is equal to 2e over 2 raised to n plus 1, or 2 epsilon. Now, actually, you can simplify that by canceling 2, factoring 2 in the denominator, so you can cancel that. You can have e over 2 raised to n. So if you're going to add all the outer measures of this collection of open interval I sub n from 1 to infinity, then we have this equation. We have this equation now. and that's equal to the summation of, since we have found the length of I sub n, that's the summation of 2 epsilon over 2 raised to n plus 1. Now, as you can see, na-cancel na. 2 was cancelled here, and that becomes epsilon. Epsilon was factored, and 1 over 2 raised to n. Take note that the summation of 1 over 2 raised to n from 1 to infinity is a geometric series. If you're going to find the sum of that, that's equal to 1. So 1 times epsilon is equal to epsilon. So that implies that the measure of A is less than epsilon. Okay? How can we say so that the measure of A is less than epsilon? Because if you're going to go back here, A is a subset of the union of all open intervals covering A, the union of In. As you can see now, by monotonicity, if A is a subset of B, then the outer measure of A is less than or equal to the outer measure of B. So since here A is a subset of the union of the open intervals covering A, so the measure of A, the outer measure of A, must be less than or equal to the outer measure of these In, or the sum of the outer measures of In. Since we're looking for the infimum, and this E actually is greater than 0, so we can say that the measure of A, or the outer measure of A, which is a countable set, is now 0. And this corollary is now proved. And you can see this illustration also. Now, if we're going to proceed, corollary number 4, the set 0, 1, or the closed interval from 0 to 1 is not countable. Now, how can we do this? Simply by using corollary number 3. No? If you're going to observe in the previous corollary that if a set A is countable, then M star A, or the outer measure of A, is 0. Take note that if that conditional is true, then the contrapositive is also true. Since we have proven that conditional to be true just a while ago, if we're going to get a contrapositive of that, if M star A is not equal to 0, then A is not countable. So the set 0, 1, or the interval, since the interval from 0 to 1 is given, so we can now find the outer measure of that interval from 0 to 1 by subtracting the endpoints. Now the measure of 0 to 1, or the interval, the closed interval from 0 to 1, is now 1 minus 0, and that's equal to 1, which is not equal to 0. Using the contrapositive of corollary number 3, since M star A is not equal to 0, we can say now that the closed interval from 0 to 1 by the contrapositive of corollary number 3 is indeed not countable. So QED. So QED stands for Quod erat demonstratum. That means the theorem, the corollary, or the proposition has been proved. Okay? Now if you're going to apply this, no, in terms of irrational numbers. So for example, what is the outer measure of the set of irrational numbers in the interval from 0 to 1, or the closed interval from 0 to 1? So we are going to find the outer measure of the set of irrationals. Now, let's try to consider this. Let A be the set of irrational numbers, no? From 0 to 1, the closed interval. Since A is the set of irrational number from the closed interval 0 to 1, then we can say that A is a subset, no, of that interval. By monotonicity, if A is a subset of B, then the outer measure of A is less than or equal to the outer measure of B. So meaning, the outer measure of A now is less than or equal to the outer measure of that closed interval. Since the outer measure of that closed interval is 1, so we can say that M star A is less than or equal to 1. Now, if you're going to illustrate that, if that is the interval from 0 to 1, consider these points as irrational numbers, for example, but without loss of generality, because there can be other irrational numbers aside from these 3 points. So we can say that that set of irrational numbers is equal to the interval from 0 to 1 minus the set of rational numbers within that interval. Now, we're going to use the notion of these rational numbers. Let Q be the set of rational numbers in the closed interval 0, 1. Now that you know that the closed interval 0, 1 now is the union of A and Q. Why? A is the set of irrational, Q is the set of rational from the interval 0 to 1. That's why you're going to get the union that's equal to the interval 0 to 1. Now, by the countable subadditive property or proposition 2 in the book of Royden, that the outer measure of the union or the whole does not exceed the sum of the outer measures of the parts, meaning the outer measure of A union Q is less than or equal to the outer measure of A plus the outer measure of Q. Now, if you're going to do that, the outer measure of A union Q, since we have established that it is equal to the interval 0 to 1, is equal to the outer measure of 0 to 1, which is equal to 1, and that is less than or equal to the outer measure of A plus the outer measure of Q. Now, if you can remember, we have established in the previous lessons that Q is countable. And by corollary number 3, if it is countable, the outer measure of 0, meaning the outer measure of Q is 0. And if you're going to go back to this inequality, substituting m star q is equal to 0, 1 now is less than or equal to m star a plus 0. Now, since we have established in our first argument that m star a is less than or equal to 1, and now we have established that 1 is less than or equal to m star a, that implies that m star a is equal to 1. Meaning, the outer measure of the set of irrational numbers in the interval from 0 to 1, the closed interval, is 1. And since it's 1, it's not equal to 0. By the contrapositive of corollary number 3, the set of irrational numbers from the closed interval 0 to 1, also using the previous corollary number 4, is not countable. Okay? So that's it. We're going to proceed to proposition number 5. According to proposition number 5, given any set A and any epsilon greater than 0, there is an open set O. Now, this is an open set O such that A is a subset of O, meaning this O is the set of open intervals covering A, so you can see that A is a subset of O, or proper subset, specifically. And M star 0 is less than or equal to M star A plus E. You know, there's a property of infimum relative to epsilon, that if the infimum of set A, or big set A, is equal to x, now for all epsilon greater than 0, there exists small letter a, an element of the big set A, such that x plus the epsilon is greater than or equal to a, an element of that bigger set A. So it seems that that property infimum with respect to epsilon is applicable here. Now, also, there is a G element of G delta. We know that G delta is defined as a Borel set, actually, the intersection of the countable collection of open sets, such that if A is an element of G, then M star A is equal to M star G. We are going to prove that. The proof came from the book of Royden. Given any set A and epsilon greater than 0, there is a countable collection I sub n of open intervals covering A. And since this countable collection I sub n covers A must be an element of the union of these open intervals. Now, basically, if you're going to get the outer measure of A, it's the infimum of the sum of the lengths of these open intervals covering A. Since we're talking about the infimum, M star A must be greater than or equal to the sum of the lengths of this I sub n if you're going to add epsilon greater than 0 to that M star A. Now, if you're going to let O to be the union of that I sub n, the collection of open intervals covering A, then O now is an open set because it's the union of an open interval or several open interval collection. And since A is now a subset of O is the union, now by the countable subadditive property also, the outer measure of the union is less than or equal to the outer measure of the sum of the parts, or the outer measure of the sum of this In. Meaning, the outer measure of O is less than or equal, if you're going to see here, the sum of the outer measures of In. Since the outer measure of In is also the length of In, and we have established here that the sum of the lengths of In is less than or equal to M star A plus E, then M star O is also less than or equal to M star A plus E. So we have established the first part. for the second part, that m star A is equal to m star G, now for each n, there is an open set O sub n such that if A is an element of that O, the union, no, the union of all open intervals covering A, and m star O sub n, that's the union of n intervals, no, selected n intervals covering A, that is less than or equal to m star A plus 1 over n, given that n is an element of natural number. Since we have defined now that G is an intersection of the collections of open intervals, we can now say that G is a G delta. And since A is a subset of G, we can now say by the monotonicity that the m star A, or the outer measure of A, is less than or equal to the outer measure of G. But since G is the intersection of the collection of all countable sets, so finding the intersection now, we can now say that m star A, looking at the infimum of the sum of these intervals of this intersection, and now we can say that m star A is equal to m star G. Now I'll be discussing a recently published article related to Lebesgue measure. And the article is all about non-Newtonian comment of Lebesgue measure in real numbers. It was published by Duyar and Sagir, 2017. If you're going to see, the article was published in the Journal of Mathematics 2017 and it's already gained 5 citations. So the authors are from Department of Mathematics, Duyar and Sagir, Art and Science Faculty, on Ducos Mayes University, Kurupelit Campus, Samsun, Turkey. Now, if you're going to read more about the article, you can visit in these references. So you have the DOI here. You can just click the DOI and go to the article and read more about it. So what is the significance of the article in real analysis and mathematics as a whole? The authors here would like to generalize to non-Newtonian real numbers the usually big measure in real numbers. If you can remember, the notion of length in a closed interval or a certain interval was extended or generalized in Lebesgue measure. That's why we have now what you call Lebesgue Outer Measure. For this purpose, in this paper, the author introduced Lebesgue measure in open and closed intervals or open and closed sets in non-Newtonian sense. So this is a new set of numbers known as non-Newtonian real line, and the authors examine the basic properties. If you can see later on, the basic properties of measure theory in real numbers was actually the same in this non-Newtonian real line, only that it was extended and generalized based on the notion and definition of the non-Newtonian real line. So what does it mean for real analysis and mathematics? This is another breakthrough in real analysis because Lebesgue measure extends the notion of length to arbitrary subsets of real number. No? Length actually is the difference of the endpoints of this certain interval. But in Lebesgue outer measure, it was extended to a more complicated subsets of real numbers. But now, this notion of Lebesgue measure was extended so far to another set R of n called a non-Newtonian real line. So isn't it amazing that you can also generalize measure theory or the properties of measure or basic properties to another set aside from the set of real numbers? Now let's try to explore some parts of the paper. It was defined in the paper that a generator is one-to-one function alpha if the domain is the set of real numbers and the range is a subset of real numbers. Meaning, you can say that this one-to-one function is a generator alpha if the domain is the set of real numbers and the range is a subset of real numbers. You know, it is given here that identity function and exponential function are examples of these generator functions, alpha. Why? If you can still remember, the exponential function is a function from the set of real numbers to the set of positive real numbers. So if you can see, the domain is the set of real numbers, and the range is the set or the subset of positive real numbers, and that's a subset of R. Now, with that definition, we denote now R of n, also called the non-Newtonian real line, to be the range of the generator alpha function. So basically, if you're going to consider exponential function as an alpha function or the generator alpha function, the range of this exponential function, which is the subset of positive real numbers, if you're going to consider exponential, this subset of positive real numbers as the range of exponential functions form the elements of non-Newtonian real line. So that's specific example. And don't be surprised because this non-Newtonian real line has also its own arithmetic operations, no? Comparable to the set of real numbers. If you're going to see, we have addition, we have subtraction, multiplication, division, even the order operations. Now, basically, this non-Newtonian real line or Rn has also its own definition of measure, no? Even its own definition of open and closed interval. If you can also see, some properties are also comparable to that of Lebesgue measure in terms of real numbers, but here the Lebesgue measure is extended to R of n or the non-Newtonian real numbers. So what does it imply? All proven properties actually in the paper, if you're going to read that, are generalization of the basic properties of measurement in real numbers. So the basic properties of measurement in real analysis was just extended in this new set of real line, but also called non-Newtonian real line, which is the range of a generator alpha function. So who knows, in the future, you might be the next one who can generalize. That's another breakthrough in analysis and mathematics. The basic properties of measure in real analysis to another set other than real numbers. So maybe you will be motivated after reading this article. So that ends about that article. And here's my analogy. Before I end the presentation, sometimes in life, adjustment is necessary for you to survive in a certain situation. You know, we are living things, we are human beings, and one characteristic of a living thing is adaptability. So we have to adapt, we have to adjust in the current situations for us to survive and to thrive. Like now in COVID-19 pandemic, we have to adjust for us to survive in our lives, in our learning, and to thrive at the same time. You know, we have to unlearn the usual things that we do in a conventional type of situation compared to COVID-19 pandemic. So we have to adjust our routine, our day-to-day living, and everything that we do every day for us to survive. If you're going to compare that in Lebesgue measure, you know, it's comparable to Lebesgue Outer Measure because if you're going to go back to the book of Royden in page 54, he said that this Lebesgue Outer Measure doesn't satisfy the four properties or basic properties of a measure because the measure function defines or the subset of real numbers, the power set of real numbers. When we say power set, these are the subsets of real numbers. The function from this power set to non-negative extended real numbers from 0 to infinity is not defined in every subset of real numbers. So basically, Lebesgue measure does not satisfy this function m. That's why for us to satisfy this function m, the domain, which includes all subsets or all elements of the power set of real numbers, must be adjusted and reduced, focused only to some sets, no? Some sets that could satisfy the function m. And that will result now to another beautiful and breakthrough in analysis called Lebesgue measurable sets to make that function work. So that's the analogy, no? Sometimes if we're going to force something in the status quo, in the current situation, maybe we'll be violating some properties, some rules, no? For example, in this COVID-19 pandemic. But if we have to adjust, no, in this current situation, we will survive and we will thrive. Like the generation of Lebesgue measurable sets, since the whole domain of the subsets of real numbers doesn't work, you have to adjust it such that it will work for some subsets of the power sets of real numbers. Okay? Now, before I end the presentation, also let me describe to you my real analysis journey using the abbreviations of the letters of my name, Japet. J stands for jovial, because I find this course fun-filled, enjoying, especially in learning new concepts. Awesome, because when you try to learn analysis, you will be surprised by strange terms, strange notions and conventions. But as time goes by, if you're going to learn about it, you'll be in awe and you'll be amazed that it's really beautiful also to learn analysis. Hunting, why? Because sometimes when you learn analysis, especially you cannot solve or prove a certain theorem or proposition, it still hunts you even before you go to sleep. Fulfilling. Because when I tried to learn analysis, I started at the very basic of real numbers. I thought it's very basic, but if you're going to delve into that, there are many complexities in real numbers. And when you get to understand all of this and to move on with the next lessons, it's fulfilling in your side. Exciting. Because when you learn something and you get satisfied, it seems that you want to learn more, no? It excites you, it interests you, no? It intrigues you to learn more. And lastly, top of the line. The experience, although this is the last course in my academics, in my major courses in PhD, the experience is in top of the line or excellent, stellar. Why? Because I delved into another world of real analysis, which I haven't explored before, and it's fulfilling in my side. So before I end this, these are the references in my part on corollaries and propositions and the research article. So that ends my presentation. Thank you, everyone.